NanoHub U, online instruction.
Hey everyone, welcome to lecture 411. So in the last lecture, we were talking about how to evaluate the finite element method, and we're going to continue along those lines. And so one of the key values of the finite element method that we found is that we can actually very quickly identify specific waveguide modes in the system by propagating along imaginary direction. So of course, imaginary direction doesn't actually exist, but the value of that is that it allows us to quickly attenuate modes that we're not interested in and only keep like the lowest order modes. And so this is actually kind of showing what happens in this kind of system when you propagate in this way. So you can actually see we already know the answer in advance, but then we're measuring the error of our solution as a function of the propagation distance. And so you can see that although it has like a fairly large oscillation at first with respect to the true answer, it fairly reasonably converges pretty quickly after about 40 to 50 microns in this case, which at the scale of a wavelength of 1.3 microns is about maybe 40 wavelengths, which is not unreasonable. So this allows us to use a pretty modest number of steps to get a pretty accurate solution, even if we don't know the answer, like in this case. So then here's another way to look at the problem, which is how accurate is this as a function of the number of finite element method elements? And then you can see that for this particular system in which we have actually two of the same waveguides that we talked about previously are coupled together, that the accuracy in terms of the coupling length, which is an important metric for two waveguides that are passing each other, actually converges fairly quickly after we achieve about 50 elements or so. So that kind of shows us that we don't necessarily need to just keep increasing the number of elements more and more. And so oftentimes this kind of analysis would be called a grid independence study, because this shows that beyond a certain level of resolution for your grid, then you don't need to have any further refinement of the mesh in order to get good answers. And so then if we look at what happens as a function of our step size, which we mentioned earlier, we have to kind of guess at initially if we don't already know the effective index of our mode, which probably we don't since we're trying to solve for it, then you can actually see that as a function of the step size, that you actually get a somewhat inaccurate answer if delta z is too large, but when delta z is below a certain threshold, which might be about 1, it looks like we actually get a pretty consistent answer for the coupling length. So that means that as long as the refinement is good enough, then we should be totally fine. We don't have to make delta z arbitrarily small in order to get very good answers, which is encouraging in terms of the timing of this sort of approach. And then we can apply this approach to another type of system, which is the photonic crystal fiber system. And we talked about it previously a little bit before. So this basically can have different architectures. Before we actually looked at the opposite type of system where we have air core, and then we have high index rods or holes. And then here we actually have low index holes, and then we have a high index waveguide. So this is not actually necessarily as unique as the previous type of photonic crystal fiber, because we're still guiding in a high index waveguide, but we also have a high index material out here. So you can see that these indices actually match. So we wouldn't have waveguiding if it wasn't for the photonic crystal fiber. So it's still valuable to look at this sort of structure. And then if we look at the effective index of this sort of structure versus the photonic crystal period, then you can see that, not surprisingly, as you go to longer wavelengths, the effective index of all of the modes that we choose is increasing. Of course, D is essentially the size of the rods as a function of the periodicity of the spacing. And so for larger rods, then of course we have a lower effective index, which makes sense because we have a higher volume of a low index medium. In the next lecture, we'll actually discuss in more detail what other solutions we can get for the photonic crystal fiber.